Welcome to another video. Rashid here. Today we will look into noise margins and delay propagation or delays through the cell and dependency of these two on the input sequence. Uh, so I'm not going into details of delay, power and other things. I might look into power. Um, But as I said, I think CMOS inverter basically understanding of that is enough to give you understanding of how complicated gates like and they're not very complicated, but complicated relative to the inverter and sorry NAND, NOR, and OR type of cells work. But there was one thing that I wanted to mention, which is a little bit different. That in the inverter case, we have one input, one output. But in the case of NAND or NOR, where was our NAND? Yes, so this is our NAND. This is NOR. I had it right in front of me. So in this case, you don't have single input. You have multiple inputs, but single output. Output is here. Okay. So you can have a delay from A when A changes to output changes, or B to output. I mean, you can have maybe A and B change at the same time, or maybe they don't change at the same time. For example, yeah, let's look into that. Let's look at and the effect of that on noise margin and delay. So that is the topic of today. So you will get it in you will get hopefully good understanding of it. So give me a little bit time to explain you that. So let's look into noise margin first. Do you remember this transfer characteristics where I drew V out with respect to V in, and it was something like this for the inverter case. Now here I have three. I explain that in a minute. So this is our NAND, okay, and the NAND truth table is like this. You follow me? Let's consider a situation where for all these inputs we have 1, and when you have A, B both 1, then output is 0. So let's say the NAND output here makes a transition from 1 to 0. So that means there are three possibilities. So we have a situation before, what A and B were before, and what A and B after. Okay, after is simple. Since we are going into 0, so both A and B has to be 1. So you can see that after A, B are 1, 1, 1 in all these three scenarios. But the scenario is the previous, it was 1 and now it's 0. So before you can have, maybe we had 0, 0 or 0, 1 or 1, 0. So these are the three scenarios I sketch here. And let's look into it one by one and see the impact of the noise transfer characteristic, and that will tell us the margins. Like remember that this one is how much it can vary all the way here, right? So this whole thing is kind of your noise margin low, and how much that gate is tolerating an input low. So if this is, again, I did a previous video on it, but no, previous or the one before, yeah, on the noise margin. So you can search with the noise margin. So if this is small, that means very small variation, very small voltage swing on the input side will be tolerated, mean that will be translated to 1. If it goes beyond that, it will get into the transition time. But there is a big one, means the bigger the more time we have here, means larger swing on when input is 0 and output is 1 will be considered or will be handled by the gate. Let's look into the first gate. Hopefully I'm not confusing you. When A0, B0 and both switch to 1. So already at, okay, yes. So it was at 0. This was 0. So this was off, this was off. This was on, this was on. With these two on, this is a pretty strong pull for this node to stay connected to VDD, because now two transistors in parallel are fighting to maintain a logic 1 there. And now when this becomes A and B both 1, so these two will fight this node to go away from it. So these are powerful means, they might not switch that easily. So this A over here means that this is the much longer in this region, so much harder for this one. So that means this for this transition, it's actually any variation on zeros will be, even a bigger variation will still be handled as 1. So you can see the higher noise margin on the low side, but there will be lower noise margin on the high side. Think of this one 0, 1. So in this scenario, B was already 1 and A was 0 and then becomes 1. So one of them was on, so it's not as strong as the both of them. But B was already 1 before. When B was 1, so this gate was conducting. So this was on, there was a small resistance of this cell. And this gate was initially 0 and now it's turning on with this situation. But here is an important thing. The bulk of these transistors is connected to ground. Do you remember that? Source is connected to ground, bulk is connected to ground. So bulk and source were at the same. And for this transistor, yes, that is the case. But for this transistor, this is on. This node is not exactly at 0 because there is a little bit of resistance. There is a voltage drop there. So this will be at a little bit higher voltage than 0. If it's higher voltage than 0, there is a voltage difference between source and bulk. An important thing is, this is something I didn't cover so far, but what you need to remember, the threshold voltage of a MOS is a function of this voltage difference. I'm not writing that detailed formula. You can find that in the books. But that is the key thing. Higher the, sorry, this is source to bulb. So higher this voltage, higher is the threshold. So threshold of this transistor is higher than this one. So this will take longer to go to ground, sorry, to turn on. So that means this point will stay longer at output VDD, but it this time will be less than these two strong ones. Of course, it really depends on the drive strength, but I'm just assuming they all have equal drive strength. Then these two will be, this will be like A case was actually stronger PMOS. The longer further into this one means stronger PMOS. The further into this one is a stronger NMOS. So this one has a stronger PMOS, but this B scenario is after that. C scenario is that A was already on. Now B, this threshold voltage is the default threshold voltage. So as soon as B1 is on, it will quickly turn this on and we will quickly have this ground. So C represents kind of have the least amount of low noise margin. Okay, again, if noise margins are confusing you, please watch my video on noise margin. That would really help you, I think. But let's look into the same thing happens in propagation delay. Normally propagation, so exactly same scenario we're looking at. Same gate, same truth table. And we are also looking into 1 to 0 transition at the output. Now this time we're looking from the delay point of view. We don't have a transfer characteristic. So let's say this was our input voltage. Could be A, could be B, could be A and B both, but I'm just sketching one waveform. Okay, so input goes from 1 to 0. So we have again three scenarios. So A and B were both 0, 0, and they both switch to 1, 1. Actually, they will switch. I mean, I'm just saying, okay, 1 to 0 or 0 to 1. It's an inverting output, right? So if output goes from 1 to 0, mean input was 0 to 1. So I should have here 0 to 1. But it's the same concept, not a big deal. Or maybe this picture is written. Just think of that. There is a 0, 1 transition right here. Scenario B is B stays at 1. I think it's the same scenario as before. Yeah, A, B, C are same. And A value changes from 0 to 1. In C case, A was previously 1, B 0. And the same thing here. It will be interesting here. The A, now this is V out, this is with respect to time. This is not V out with respect to V in. This is really the waveform of output with respect to time. So this, remember, this was a strong case for PMOS. And our signal is making 1 to 0 transition. So what I have here, that, this doesn't look right. Okay, input goes to, let's fix first of all this one. Sometime when I write it, I don't realize it, and only when you teach stuff, that's where you realize you made a mistake. And I don't have time to record everything again, so let's see if we can fix it live. Okay, let's make sure. Maybe this thing created confusion for me. Right? Our inputs are changing 0 to 1. And after is both A and B becomes 1. Only then it transfers. So this pink guy is the very first one. And what I'm saying is that it will quickly come to 0. I think that is not the case, because since A and B, when both are 0 and both go to 1, there is a strong pull to VDD. So this will be slower to go to 0. You can rub that. Okay, you guys need to check with me if the logic that I am mentioning makes sense. I would say this will make the slowest transition. Then second one, this one, the next one making slower transition, because as for the same reason, this takes longer to turn on. So it stays more in this. Basically, it's the same concept of noise margin. Exact value really depends on the signal and all that. Just think of some relative values. And the last one is, so same explanation holds. Let's put it this way. This is A, okay, B, and C. Make sense? This scenario is, this is the worst case for N turning to ground. Yeah, well, that's fine. Then both A1. So this will be the slowest then B is after that slower, then C will be the best case for ground because this was already one. We just put one here turned in and only one of the transistor. Okay, I think this makes sense. Hopefully I did it right. But keep in mind, okay, so far when I was doing combinational circuit and sequential circuits, I didn't touch timing. I think with the CMOS knowledge, we already look at CMOS inverter propagation delays when you have interconnect. So for these type of gates, combinational gates like NAND we have here, the delay is from input to output. In inverter case was simple, A to output. But we have A and B. So for these type of cells, typically the term uses timing arcs. It's a timing within the cell. So this is one cell. This is one standard cell. It's called NAND. Typically NAND is a pretty common one. You sometimes assess the number, this design is equal to how many NAND gates. Okay, what is the NAND area on a process node 65 versus 45 versus 32, 16, blah, blah. That tells you relatively the size of the technology, a rough way to speak. And a rough way to speak on the size of the overall design. Okay, my design, this PCI controller has 1 million NAND gates. Oh, another design has it. So it's kind of good, roughly can give us a relative size of different designs. But the important thing is there are within the cells a timing arc. The delay, which is timing arcs or the timing delay, is A to out can be one, B to out can be another one. It really depends what the previous value of A and B were. I mean A to B, these two are connected together. So it would really be the what is ever the worst delay. And there will be A rise, output is fall. So it's a negative unit. Input is rising, output is falling. So there will be a delay at the output, a fall delay with respect to A, and output will also have a rise delay with respect to a falling A. So this is one timing arc. Okay, this is another timing arc. This to this doesn't exist. That's not a valid timing arc. So rising A to falling out, falling A to rising out. So there are two timing arcs. Okay, it's one's timing arc, but it has two components, rise and fall. Similarly for B to out. So whenever later on in physical design we'll talk about timing arc, keep in mind that is for the cell case, that is really from its one of the inputs to output. That's the timing arc. We measure it typically with this one. When they characterize it, I mean, I remember I gave you an equation too for a rough measurement, but if somebody wants to do a SPICE simulation, you have an input and output. So measure from 50% point to this 50% point, and this is really timing arc delay or timing delay for this timing arc. And we will look into standard cell library, how this information is kept in standard cell library. Actually, I tried to give it, but I'm going to skip that. I will cover that in the physical design section, which is coming pretty soon. Let's look into AND gate and OR gate. So NAND we look at, in order to make AND, all you do is you put an inverter there. And OR, you have NOR and you put an inverter and becomes an OR. The same timing arcs, they exist from A to out here, B to out here. But in this case, there's an inverter here, so you will have rise to rise, fall to fall type delay, but the rest is the same. For each, you will have a rise, output rise and fall with respect to input, output rise and fall with respect to this. So two timing arcs. Yeah, this part I will cover in the standard cell when I talking about the library, how standard cell information is kept within the library. So we'll look into in the physical design part. This is just a CMOS. Okay, yeah, I think that's it. In the next lecture, we will cover latch, flip-flop, how those are made with these type of gates, and we will talk about setup and hold time there. So that's it for now. Thanks so much for watching. Bye.